The topics I'm going to cover here is molarity specifically, and looking at how to make dilutions, mass volume percentage dilution, or a volume to volume percentage dilution, and then we'll go over an example problem, something you might see in the test. So concentration, hopefully this is a quick review for all of you. Something molarity is defined as moles of solute per liter of solution. And usually when you're working with a concentration or something, I put an example here, toluene blue, you can usually look up the molar mass, concentrations grams per moles. So I put a link here, toluene blue. This just goes to the Signal Aldrich website. Usually when you buy chemicals for a lab or something, they provide details like this on their website of compounds. So you can look up the molecular formula grams per moles. And on here, it's very small. Down here, it says 373, so I highlight that for you. So what we're looking at is the molar mass. Just a side note here, when you also look up chemicals, it's very important to also look at things like the MSDS, so the safety spec for these chemicals, again, which can be found right on the website. So if you look at dilutions, a mass volume percentage, a typical example here, it's actually defined as mass of the solute in grams per 100 milliliters of solution. So if you look at something like a salt concentration, a salt solution, we put 10 grams of salt in 50 ml of water, we get a 20% solution. So that should be pretty straightforward, right? 10 over 50, 1 over 5 is 20%. A volume per volume percentage is defined as the volume of solute in milliliters per 100 milliliters of solution. So if you look at, again, a simple example, 70% ethanol is a very common volume per volume percentage. You take 70 ml of ethanol, add 30 ml of water, and you get 70%. So again, that should be really straightforward for you guys. And if anyone would need any further explanation on that, I'd ask you to talk to me after class. So some really quick notes here that are very important. In concentrations here, you need to remember that the divisor is always the total volume of the solution. So going back to my ethanol example, it's 70 plus 30, but the divisor is 100. So it's 70 ml of ethanol in 100 ml of solution, giving you that 70%. The other thing I need to consider, especially in a laboratory setting where I work, where I teach, you need to consider what you can measure and what you can't measure accurately. Your dilutions aren't going to come out right if you can't accurately measure them. So if you're given a pipette aid like this, you can probably measure something like 10 ml, but you might not be able to measure 100 microliters. Working with pipettes like this, you can't measure anything accurately with a full pipette, so you wouldn't use those for accurate piping. What you would use is something like these. These are microliter pipettes, so there's a range of microliter pipettes for different volumes of solutions. The last thing that you really need to consider as well is what are you limited by? What are your limiting reagents? So again, going back to my ethanol equation there, if I have 70 and 30, that gives me 70%. That's very true. The math works out great, but I can't add 70 ml of ethanol to a vial that only holds 10 ml. So I need to be conscious of what I'm limited by. If I have a 10 ml vial, I can't use 70 ml. I'd have to change that concentration to 7 and 3, right? Give me 10 total. So you need to just be mindful of what you're limited by. So here's a typical example of a problem you might see on an exam or a test. If you're given a 1% mass per volume solution of toluene blue, given the molar mass, how would you calculate, make a dilution at 4 micromolar using distilled water? And for this calculation, you're given a 50 ml tube for this dilution. So I'm going to go over this with you really quickly. The first thing we want to pull out of this equation, pull out of this word problem, is 1% mass per volume. So you heard me mention mass per volume is defined as grams per 100 ml. So 1% doesn't tell me much if I'm trying to get to millimolar, right? So what I can do with 1% is I can actually pull out a mass and a volume. So 1% just translates to 1 gram of toluene blue in 100 ml of H2O. So I've got, everyone follows me on that, right? Pretty straightforward. Again, now I've got my mass and my volume, 1 gram and 100 ml, but I'm trying to get to a molar concentration. So I'm just going to convert that mass and volume into molarity. So I use the molecular weight that's given there, 374 grams per mole, and I convert this, and number 2 here, to a molar solution. So I take my 1 gram, multiply by 374 grams per mole, divided by my 100 ml, which just obviously is 0.1 liters. Molarity, remember, is defined as moles per liter. That gives me my molar concentration. And you can convert this similarly from moles to millimolar, just multiply by 1,000, obviously. So now, again, going back to my word problem, what do I need to do? What's the next step? So this was a mass per volume dilution. What I need to do, though, to make my 4 millimolar is actually make a volume per volume dilution. So if I look at my word problem, I've got a solution of toluene blue, and I'm using distilled water again in solution, so I'm using 2 volumes here. So what I do is I make an equation, as in step 3. I need some volume, unknown, times what I have currently, the 26 millimolar, that's my 1%, divided by, again, some volume, which I don't know, to make my 4, which is what my target is. So how do I go about doing this? So I have a simple equation, but there's 2 unknowns. I need to pick one of them and just define it as something. So what am I limited by? That's what I told you before. I'm limited by my 50 ml. So I'm limited by the total volume I have. I can only put 50 ml. I can't pick X to be 100 ml because that's not going to fit in my tube. So the best thing to do here is pick your total volume, your Y ml, as something that's reasonable. So I'm going to pick 20. And again, now I have a simple equation. I have one unknown. Very straightforward to solve that. So if I just mathematically solve the equation for you, you'd get X equals about 3. So I'm done, right? Who agrees with me by a show of hands, just assuming my math is correct? If I take 3 ml of toluene blue, where's my mouse? There it is. 3 ml of toluene blue and I add it to 20 ml of water, I'll get my 4.0. See a show of hands who agrees with me? You guys follow me there? Okay, anyone that raised your hand, you're wrong. And this is where I typically, this is what if you take one thing away from my talk, this is what I'd really like you to concentrate on. My notes there, the divisor is always your total solution. So I can't take 3 into 20, I actually have to take 3 into 17. So the answer to my word problem here is not 3 and 20, it's 3 and 17. And this is where a lot of my students go wrong, so I try to make sure I highlight this and tell them this when they're making calculations in the lab. So again, what I'd like to highlight here is the divisor. Very simple equations, very simple math, it seems straightforward. A lot of students, when they do it mathematically, no problem. When they go to the lab and they try to do these things, they take 3 and 20 and their answer comes out wrong, which I can actually test on a microplate reader. So you need to make sure that you're conscious of what you're actually doing in the lab. So if I was going to test you, I know we're out of time, that's my 7 minutes is up, but I would have an example problem to give you a test to hone your own skills.